Varshney, and I'm a researcher at IBM Research, and with Manning Publications, I'm writing the book Trust in Machine Learning. And the book is it's a pretty interesting book in my opinion, and it's already available on the early access program of Manning, the MEEP. So 8 out of the chapters are out there already. So you can go and check it out, get those chapters as an ebook, and then take a read, give me comments as well, and I'll take those comments into account as I keep revising it and working on the other chapters. So when I say trusted machine learning, what is that all about, right? So machine learning, or artificial intelligence, of which it's a part, AI, is powering lots of critical workflows, and trust is really essential in all of that. So those workflows include things like loan processing, employment, customer management, quality control, and many, many others. And there's many factors that are placing trust in AI as a top business priority. So things like brand reputation is a big reason, increased regulation, complexity of AI deployments, and these days especially, there's a renewed focus on social justice. And as an example of the increased regulation, just a couple of weeks ago, the European Commission came out with some draft regulations for saying that if AI is used in high-risk applications, it has to be controlled. Right? So what does it take to trust a machine when it's making those decisions for you? So the first thing is that it needs to be accurate, because without that, you can't really do much of anything else. But then there's lots of considerations beyond accuracy. So machines have to be fair, they have to be easy to understand, they have to be transparent, so throughout the life cycle, and then they have to be robust and secure so people can't tamper with them. They have to know kind of when they don't know, so have some level of humility as well. So in the first chapter of the book, I actually go through and define what trustworthiness means very specifically. So I kind of rely on the organizational management literature, and in that literature, talking about trustworthy people, folks have come up with 4 different attributes, which can also be related to trustworthy AI and trustworthy machines. So the first attribute is that people are competent or credible at what they're doing. The second is that they're reliable, that they have integrity. The third is that they're open, that you can communicate back and forth with them. And the fourth is that they're selfless in some capacity. They're not only working for their own goals. So all of these things map to machine learning. So the first attribute of competence means that the machine learning system has to be accurate. The second attribute is related to distributional robustness, fairness, and adversarial robustness. The third attribute relates to explainability, for us as people to be able to understand the machine, transparency, so that the entire pipeline is made available to us, and then the other direction, us instructing the machine to what our values are. And then the fourth attribute is mapping to AI for social good and empowering people to use AI in ways that meet their goals. So the main message that I want to give throughout this this Twitch session is that don't take shortcuts, okay? And that's the way that you'll be able to build trustworthy AI. So on the right, we see a diagram. This is from chapter 2 of the book. So there's several phases as you're developing machine learning. So there's a problem specification phase, a data understanding phase, data preparation, data modeling, then evaluation, and then deployment and monitoring. And there's different people involved in different stages. There's the problem owner, the data engineer, the data scientist, model validator, and AI operations engineer. And there's another persona on here that is normally not there. It's diverse stakeholders. Okay? So the shortcut that people often take, almost always take actually, in the problem specification phase, when you're trying to figure out, should I even do this problem using machine learning, is not to take advice from a panel of diverse voices. Because if you're a person in power, you are probably going to have a lot of blind spots that people who are from vulnerable and marginalized and minoritized groups don't have. They see issues that the people in power don't. So there could be a particular problem you're working on, and it's actually, if you use machine learning in that, it can become an instrument of oppression or violate human rights and stuff. So you don't want that to happen. Even if the problem itself is okay to pursue, what are the considerations that you should have as you're developing it? So those are things that a very broad-based set of folks can give you input on. Right. The second and third parts of the life cycle are data understanding and data preparation. So this is an image or figure from the third chapter of the book, or actually the fourth chapter. And it's kind of showing that there's a lot of biases that can come in when you are working with data. And you actually can take the shortcut of just taking whatever data you got and just running with it. But what you really should do is go back and try to understand where it came from, what sort of biases did it have, and did it pick up along the way. So the first process that happens is measurement. So this is where you're figuring out what features that you're going to use in a machine learning sort of model. And there's a lot of social biases that can crop up here. So one example I like to use is the SAT score, which is used in college admissions in the US. So that exam actually has a lot of questions that are harder for people from certain backgrounds to answer. So the score that they get might not actually reflect the true underlying ability for them to succeed in college. So that's an example of a social bias. And then once you have your features figured out, you're going to sample the data, actually collect those features for individual people. And there can be sampling biases here. So the population itself, you might underrepresent or overrepresent certain groups. And you can also have temporal biases. So maybe you collected the data a few years ago and it's not valid anymore. So data from pre-COVID is a great example of data you don't want to use in a lot of applications in the post-COVID world. And then once you have your data points, you're also going to do some feature engineering, some data preparation. And there's things that can crop up there as well. So there's data preparation biases, and an adversary can actually poison your data as well. So what's an example of a data preparation bias? So sometimes you're actually doing data engineering where you put together features from different sort of columns all together into one big feature. And while you're doing that, it's possible that you would lump together things that actually lead to biases that weren't there before. So one example of that is if you're building a model to predict healthcare costs for the reason of allocating extra preventative care to people. First of all, you shouldn't actually be using healthcare costs because you want the most deserving people to receive the care, which are the people who are the sickest. And in a US context, for example, certain groups like African Americans are actually utilizing the healthcare system less for the same level of illness as other groups. And when you're doing that, if you use the healthcare cost, lump it all together, then it leads to a kind of a bad situation. But when you leave different healthcare costs separate, so emergency room costs separate from inpatient costs, separate from outpatient costs and stuff, there's actually not so much bias that comes in. So there are choices that you make subjectively that lead to this as well. Then the next phase is modeling. So on all these different pillars of trust, general robustness, adversarial robustness, fairness, explainability, uncertainty quantification, and so forth. There's different sort of things that you can do. So there's pre-processing, model training, post-processing, and each of these different sort of pillars of trust have ways of mitigating bias in modeling, so or mitigating the issue. So the shortcut is just to take the training data you have and just run your normal model training thing, and that's it. You don't do post-processing. You don't introduce extra constraints in the model training. You don't do post-processing, and then you end up with bad models in the sense of trustworthiness. So let me show you an example of how to do this with fairness, right? So fairness is all about systematic disadvantages to certain protected groups or individuals that come from all the things that we talked about. Problem is specification, data preparation, historical prejudice in data, and under or oversampling. So here's a demo. So we're going to look at a particular data set, and this demo is coming from an open source toolkit called AI Fairness 360, which includes a lot of Python code and Python notebooks as well that you can use in your natural workflows. But I'm going to show a sort of visual example just because it's easier to convey what's going on in a more gentle way through this. Right? But all of what I'm showing can be replicated in code, and there's notebooks on this site that show you how to do it as well. All right, so let's pick a data set. So this is one called the Compass data set, and this is coming from a criminal recidivism sort of use case. So what we're trying to do is predict a criminal defendant's likelihood of reoffending. And we need protected attributes. So we look at two different ones, sex, where females are the privileged group and males are an unprivileged group, as well as race, where Caucasians are a privileged group and non-Caucasians are an unprivileged group. All right, so let's see what happens when we check for bias on this data set. Okay. So if we look at a few of these fairness metrics, statistical parity difference is one, equal opportunity difference is another. We see quite a bit of unfairness according to sex, because a value of 0 would be a completely fair situation. And similarly with race, again, we see unfairness because there's a non-zero value here. Good. And these fairness metrics actually encode different sort of things. So statistical parity difference assumes that there is social bias, and so it's a metric that makes sense when there is social bias. Equal opportunity difference is a fairness metric that is the right one when there is no social bias and only sampling biases. Okay. In any case, we see different sort of biases that are objectionable. So the next thing we want to do is actually to mitigate that bias. Let's use one pre-processing approach called optimized pre-processing. I'm actually one of the inventors of this method. And if we do this, let's see what happens after we've done the mitigation. Okay. All right, so what happened? So we've gotten closer to 0 with statistical parity difference and equal opportunity difference, but it's not gone away fully. And the reason for that is we also want to maintain some level of accuracy. So initially the accuracy was 66%, and it's dropped to 65%, which is somewhat negligible. So we've done something good, gotten closer to fairness, but not all the way. Right, and when we look at race, we actually get really close to 0 for statistical parity difference and for this average odds difference. So we've gotten really fair, and in fact, it's almost kind of hard to believe, but the accuracy has slightly gone up, which isn't, so meaningful. The main thing is that it hasn't dropped, but we can mitigate these biases quite well on the race attribute. So that's an example of fairness and how to mitigate biases. Right, so now if we go to our next topic, which is explainability. Right, so here the idea is that we as humans want to be able to understand how it is that the machine learning models make their decisions. And there's not one best explanation for all kinds of consumers of those explanations. So loan officers and regulators and affected users and data scientists or developers have different needs in those explanations. So let's see a demo of this as well. Okay, so this is a lending example coming from another open source toolkit, AI Explainability 360. And the use case is lending, like we just talked about. So specifically, this is a data set made available by FICO, which does credit scoring. And it's an anonymized data set related to home equity line of credit applications for mortgages. So as we just talked about, different consumers have different needs in their explanations. So let's start with a data scientist who needs to ensure that the model works appropriately before deployment. So what a data scientist wants to understand is what's the overall logic of the model in making decisions? Is the logic reasonable? Can we deploy the model with confidence? So one approach for understanding is a directly interpretable model. So this comes in the model training phase. And specifically, we're looking at a model called the Generalized Linear Rule Model. And this was invented by Dennis Wei and colleagues at IBM as well. So here, the rule itself, or the model itself, is easily understood by people. So there's actual features that we can look at in terms of the rules that they have to follow. So there's this one feature called external risk estimate, and for every increase of 10 in that value, the score, so the more likely someone is to be a good sort of lender or borrower, I mean, is increased, right? And then that changes for different sort of values of this external risk estimate. So as a people, we can really understand exactly what's going on, right? Similarly, for this other one, net fraction revolving burden, it actually goes in the other direction. Okay. And the months since the most recent delinquency, again, has a particular sort of value that it contributes to the overall model. And these guys get combined with coefficients that are indicated by the green and the red bars, and this is a rule that we can very easily understand. Right? So now let's say you're the loan officer. So what you need to do is assess the model's prediction and understand why the model is predicting something for a given applicant, right? And it should be helpful for you to make your personal decision to accept or reject, right? And here we're going to look at similar individuals. Okay? So this is an algorithm called Protodash, invented by an IBM researcher named Amit Dhurandhar and his colleagues. And let's look at one of the applicants named Alice. Okay. So Alice has this particular set of features. So 3 of them we saw before. This is the whole set. And we can look at different other customers that the algorithm has found, Mia, Kate, and Kayla, and all of them fully repaid for their loan, and that is why Alice is predicted to be approved by the machine learning system. And we can see that Alice is similar in many respects to these other customers, and that gives us confidence of what's similar and different about Alice compared to these other customers. Robert is predicted to be denied, and we can find 3 other customers, James, Danielle, and Franklin, who all defaulted on their loan, and they have various sort of similarities and differences to Robert. So again, we can gain some intuition of why it is that we're making these recommendations from the model. And finally, if you're the bank customer, you applied for the loan, you want to understand what happened. Specifically, you care why was my application rejected? What can I improve to increase the likelihood my application was accepted, and so forth. So this is an algorithm called contrastive explanations method, also invented at IBM Research by Pinyu Chen and colleagues. So let's look at Jason, one of the applicants for whom there was a denial decision. So here we see that there's 3 different factors. The consolidated risk markers were 65, but they needed to be 72 for the application to be approved. The average age of the accounts was 52 months, and it needed to be around 68. And the month since the most recent credit inquiry not within the last 7 days was 2 months, and it needed to be around 3 months for the application to be approved. So this gives you a sense of the recourse that Jason needs to go undergo. And similarly for Anne, we see a particular set of recommendations, and for Julia as well. So different factors and what she needs to change in order to maybe be approved. Okay. So that's all about explainability. And the next topic is adversarial robustness. Okay. So here the idea is that there's a bad guy, and that bad guy is trying to attack you, try to do something malicious. So there's the data poisoning attacks, which we talked about before. So they're trying to poison your data set so that the model that's learned is favorable to them somehow. Okay? And there's the evasion attack, in which you start with a model already, but what the bad guy does is they feed in some weird sort of data input, which looks normal, but actually has some specific weird characteristics that trick the model into doing what the adversary wants. And it's this adversarial robustness is ways to defend against those malicious attacks. And they're not only for looking at malicious attacks, but also pushing AI to its limits as a test. Okay? So let's look at an example of this as well. So this is an example coming from the Adversarial Robustness 360 toolkit. And this is also an open source package. The nickname of it is Art. And let's look at one of the demos for Art as well. Okay. So here the data is images. Okay. So let's look at a mousetrap image. There's a few other options in here. And there's different types of attacks that we can do for the evasion attacks. Okay? So let's just pick one of these, the fast gradient method. And if we look at the image, before it was attacked, it was classified as a mousetrap. So the model was 100% confident that this is a mousetrap. Okay, we add a little bit of noise. It's hard to see a little bit, but the image has changed a bit here. We can keep adding noise, and you can see that there's more and more like speckling and stuff happening here. And as we changed it, the classification changed from being the mousetrap to a rubber eraser to being a wallet to being pretty confidently a bath towel. And these look nothing like like a mousetrap. So just this little bit of noise, which is hard to see, completely fooled the machine learning model. Okay. So let's see the low amount of attack, if we can defend against it, right? So this is a defense with adding Gaussian noise, and if we add enough, so at low protection, it's still a rubber eraser, but now we add more noise and it becomes a mousetrap again, which is what we wanted. And if we protect it even more, it's even more confidently a mousetrap. So that was the Gaussian noise. You can see, what's happening over here. And you can also do other defenses. Spatial smoothing gets you back to a mousetrap and so forth, right? So these are different ways of defending against adversarial attacks. Okay. All right, so those are some examples. And then if we go to back to our life cycle, right? So now we're at the evaluation phase. So what's the shortcut that people take? Again, they're often in positions of power, and they don't take advice from a panel of diverse voices, especially those from marginalized groups and people who are not in power, who are vulnerable. So they don't actually see what's going wrong. They have these blind spots, and they'll say, yeah, that's fine, and just move it along. Whereas model validators who have actually experienced, have lived experience of discrimination or other bad things happening to them are more likely to see these problems. Then finally, we're in the deployment stage, in the governance stage, right? So the shortcut here is not actually ensuring that your model development lifecycle was well governed, or not actually thinking about the monitoring aspects. So here, the thing to do is actually capture all sorts of facts and all sorts of sort of information throughout the life cycle. What were the intended uses and other qualitative information? What sort of tests were done throughout? So those could be accuracy tests, but also fairness or robustness or explainability tests. And that continues on through the deployment as well. So let's look at an example of this as well. So this is a website called AI Fact Sheets 360, and this is showing you, again, the same process of the different roles in the AI lifecycle and what are the sort of facts that we can collect. So this is a use case also related to lending and home mortgages specifically. And here's the example, actually using those three other toolkits, AI Fairness 360, AI the Adversarial Robustness 360 Toolbox, and AI Explainability 360. Okay, so there's some facts that the business owner, the problem owner, is going to put in a qualitative sense. So what's the model purpose, predicting mortgage approvals, and also what's the risk level, which is high. And then there's a bunch of facts that can be automatically computed using the toolkits that we just saw. So the data scientist who's developing the model can compute their versions of these metrics, and then the model validator can compute their versions of the metrics. And they're pretty similar, and they're all, I mean, pretty good, so we can move on, right? And then what happens is that the model validator can use a different challenge model and see if it compares well or not. And it does. So our model is more accurate, has better fairness, is more robust, is more explainable, and so forth, right? And then finally, once it's in production, the AI operations engineer can check out what's going on with deployment. So there's going to be a little bit of loss in some of these things. So that happens normally in the real world. And you get to see, yeah, I mean, there's a little bit of loss in accuracy, a little bit of loss in fairness and so forth, but it's still pretty good. So that's the short, not taking of the shortcuts. Keep monitoring things, keep them going, right? So that's kind of what I wanted to go through. And this is a reminder of the book. Thank you for joining me, and it was my pleasure to be here with you tonight.